everyone, I am Christian James. So in this video, I will show you what is recursion, why and when to use it, the practical demonstration of recursion, and I will share tips and common mistakes so your recursive code is safe, fast, and easy to understand. So without further ado, let the learning begin. What is recursion? Recursion basically means solving a big problem by breaking it into smaller copies of the same problem. Instead of using loops like for or while, recursion lets a function handle a tiny version first, and then it will combine the results as the calls return. One of the main reasons recursion is powerful is because it helps us to express complex process in a clean and readable way. Instead of writing long loops or nested loops, recursion lets you describe the problem in a more natural, step-by-step style. Let me explain these three terms a bit more clearly because they are the foundation of recursion. The first one is the base case. So this is the condition where the function finally stops calling itself. Think of it as the final goal or the simplest version of the problem. For example, n factorial, when n becomes 1, we stop. If you forget to write a base case, the function will keep calling itself forever until the program crashes. This is called a stack overflow. So the base case must always be reachable, correct, and simple. The second one is the recursive case. So this is the part of the function where it calls itself again, but with a smaller, simpler, or reduced input. The idea is each recursive call brings you closer to the base case, and each call solves a tiny piece of the problem. For example, in a countdown, we call countdown, so it represents n minus 1, which slowly pushes n downwards until it reaches 0. If the recursive case does not actually move the input closer to the base case, the function will also recurse forever. The last one is the call stack or stack frames. This is how the computer keeps track of function calls. So every time you call a function, even a recursive one, the computer creates a stack frame, which is like a small container that stores variable, parameters, and the return addresses. When you call a function inside itself, another frame is added on top. So recursion creates many frames, one for each call. The computer removes these frames in reverse when the function returns. If you call yourself too many times, for example, 1,000 times without stopping, the stack fills up and the program crashes. So this is why the recursion must be designed carefully, especially with deep or unbounded inputs. Alright, let's start with the easiest possible example of recursion, a simple countdown. So our goal is to print the numbers from 5 down to 1, and then we will print the ignite BSIT. So I will copy our code, example code. Okay, so in this program, the base case is when n becomes 0 or negative. That's when we stop the recursion and we will print the ignite BSIT. Otherwise, we print the current number and call countdown again. But we reduce the value of n by 1. So this is the classic pattern. So the base case first and then the recursive case second. So, okay, let's try to run it. Okay. So notice that the function repeats until it reaches the base case. So each call waits for the one after it to finish, and only then returns. So the next example is the famous factorial function. Mathematically, factorial is defined recursive as 1 factorial is equal to 1, and n factorial is equal to n times n minus 1 factorial. So this makes it perfect for the recursion. Okay, so here's our code. I will paste it. Okay, just like the countdown example, the base case stops when the recursion. If n is 0 or 1, the function returns 1. But if n is greater than 1, we return n factorial, which represents n minus 1. So in other words, the function calls itself with a smaller number until it reaches the base case. So, okay, I will run this code. Let's see. Okay, the result comes from these chains of calls. So 5 times 4 times 3 times 2 times 1 is equal to 120. So recursion breaks down a big problem into smaller versions of the same problem. And now, let's look at Fibonacci numbers. So this is another mathematical definition that seems perfect for recursion. But as you'll see, the recursive version has a big performance problem. So in this function, the base case is when n is 0 or 1, we simply return n. Otherwise, we call the function twice, one for n minus 1 and one for n minus 2. So this is a build branching tree of calls. Okay, so I will copy the example code. Let's see. So for example, calling fib5 actually calls fib4 and fib3, and then each of those calls more functions, and so on. A lot of repeated works happens. Okay, so let's try to run this code. The fib10 for fib10. Okay, so fib10 is equal to 55. That works fast. But what if we try fib40? The program starts to get slow, which means it's because the ninth recursive Fibonacci has explanation time complexity. So I will show you my iterative version code. Okay, so I will copy. To fix the performance issue, we use an iterative version. This uses a simple loop and extremely fast, even for large values of n. So this example shows why recursion is not always the best choice. Sometimes it's elegant, but not efficient. So now, you've seen recursion in action. Countdown, factorial, and Fibonacci. So next, I'll give you some important tips, common mistakes to avoid, and practical advice for writing, and a clear recursive functions. So this is my tips when you use the recursion. The first one, always define a correct base case. The second one, be careful with types. Use long or unsigned long if factorial might overflow. Mention integer overflow to viewers. The third one, watch memory and time. Recursion holds many stack frames and local variables. For deep recursion, I prefer iterative or convert to tail recursion. Number 4, tail recursion. If a function's last action is the recursive call, some compilers may optimize it. But in C, Don't rely on tail call optimization. It's not guaranteed. Number 5. Memorize expensive overlapping recursion. Use an array or hash to cake the results. Number 6. Debugging tip. Print entry or logs, or use a small example step through in a debugger to visualize the frames. To recap, recursion can make certain problems elegant and easy to reason about. And remember, base cases, watch stack usage, and choose the right tool. Recursion or iteration based on clarity and performance. Use memoization when you see repeated subproblems. Thanks for watching, and see you next time!